Okay, this is Chapter 15, Buffers and Ksp. Historically, this is probably the hardest unit that we will do the entire semester, or actually the entire year. What we're going to talk about today are common ion effect, what are buffers, and buffer capacities. I want to let you know that this is going to cover sections 15.1 to 15.4, but I'm going to break it up into two lessons. So to do that first homework assignment in Chapter 15, you will probably need to watch the first two videos. Let's start with the common ion effect. Sometimes equilibrium solutions can have more than one ion. We call these common ions. If we were to look at just the straight dissociation of NaF solid, we know that in solution we would get Na plus and F minus. Those are the two ions that make up this compound. In this reaction, if I had HF aqueous, then that would dissociate into H plus and F minus. If I were to add NaF solid, what that does is, as soon as that hits the water, it's going to turn into Na plus and F minus. And what that essentially does is, we're not interested in the Na plus because that doesn't appear anywhere in the reaction. However, the F minus is a common ion to the F minus in the HF aqueous solution. So what that in turn does is increase the concentration of F minus, and that's going to cause an equilibrium shift to the left, forwarding the reverse reaction. So F minus and H plus would be colliding more and combining to make more HF aqueous. So what is the percent dissociation of 0.1 molar solution of acetic acid? Now this actually is from the last unit. This is Chapter 14, but we're going to use this as a lead-in to the following problems that we're going to be doing. So this essentially is a review. First of all, we need the Ka for acetic acid before we begin this problem. Our Ka is 1.8 times 10 to the minus 5. So let's write a dissociation reaction. I am going to use the other form of acetic acid, which is HC2H3O2. Can be written both ways. This is the old school way. So we have HC2H3O2. We know this is a weak acid because it's not one of the 6 strong that you had to memorize. Therefore, it warrants a double arrow, and C2H3O2 minus. So in our ice table, we have a 0.1 molar solution, and we have no dissociation at the start of the reaction, minus X plus X plus X, 0.1 minus X, and X and X. Therefore, our Ka is equal to 1.8 times 10 to the minus 5 equal to X squared over 0.1 minus X. Again, the easiest way to do these problems is using your solver. However, you can realize that this X, because this Ka value is so small, that this X is also going to be very small. And if you just wanted to solve it algebraically, you could get rid of this X and just solve algebraically for X using the X squared. I'm going to put it in my solver, and I'm going to get X equal to, which remember is the hydrogen ion concentration as well as the acetate ion concentration. I'm going to get X equal to 0.001 molar. So they want to know the percent dissociation. Remember that percent D is part over whole. Sometimes it's called percent ionization or percent dissociation. It means the same thing. Our point is our X, our part, is our X. Our whole is 0.1 times 100, and I'm going to get percent. dissociation. Now, it's possible that when you got your x here, because you should be doing this with your solver, some of you may have gotten an x equal to, if you took the whole number, 0.00133, and that's fine. If you use this as your part, then you would have gotten a 1.3% dissociation. Still, again, very small dissociation due to the fact that it's a very weak acid, and we know that weak acids don't like to dissociate, which is lended to by the Ka value being so extremely small. Okay, so this was our lead-in. So now we're going to look at a common ion problem. It says a mixture that contains 0.1 molar acetic acid and 0.1 molar sodium acetate. Right off the bat, you know that we're not going to be interested in the sodium part of this. We're really only interested in the acetate ion because that's the only thing that has anything in common with acetic acid. So I'm going to rewrite what we just did to show you what a common ion does in solution. So C2H3O2, H plus, and the acetate ion. And I'm going to set up my ice table. So initially we have 0.1 molar acetic acid. However, I also have 0.1 molar acetate ion, and I have no hydrogen ion yet because the sodium acetate was mixed with the acetic acid. So my change is still going to be, as the acetic acid tries to dissociate, minus x plus x plus x. So now at equilibrium I have 0.1 minus x, x, and 0.1 plus x. I'm using the same Ka value, so my Ka is going to be equal to 1.8 times 10 to the minus 5, and now I have in the numerator 0.1 plus x times x over 0.1 minus x. And that's going to equal my hydrogen ion concentration. So x is equal to H plus. It's also equal to my acetate ion concentration, but I'm really not interested in that right now, but I will write it down. And that's going to give me a value of 1.7995 times 10 to the minus 5, which for all intents and purposes we can approximately call 1.8 times 10 to the minus 5. So that's my x value, and then I'm going to calculate percent dissociation. So I have 1.8 times 10 to the minus 5 over my original of 0.1 times 100. And that's going to give me a percent dissociation of 0.18%. So you can see the difference. Here I was 1 to 1.3% dissociated, and now I'm only 0.18% dissociated. This should make sense because here the dissociation of the weak electrolyte, meaning the acetic acid, is decreased by the addition of a strong electrolyte that has an ion in common with the weak electrolyte. So my weak electrolyte is the acetic acid. I added a strong electrolyte, sodium acetate, which contained an ion in common, which was this. So essentially, I increased the acetate ion, which caused a shift to the left, shifts left, favoring the reverse reaction, which is going to slow down the dissociation of the acetic acid. Also, before we get started here, I want to remind you in your textbook in the appendix on A23. A23 in your appendix are the commonly used Ka and Kb values that you will be using. And you should be pausing me after we do a couple of these problems. You should be pausing me, trying to do them yourself. You should be working them through on your solver, making sure that you're getting the same answers. Just watching me do them is not going to ensure that you know how to do them. Okay, so let's look at this problem right here. Calculate the fluoride ion concentration and pH of a solution that is 0.2 molar in HF and 0.1 molar in HCl. And they gave you the Ka value. So I want you to pause me and I want you to go through the steps that I just went through on the acetic acid problem and see if you can come up with an answer for this. So you've done that. This is what you should have gotten. First of all is your reaction. HF plus water yields H3O plus F minus. Now you didn't have to add the water. It's simply acceptable to say HF aqueous yields H plus and F minus. That's fine. This is just another way of writing it. Some people like writing the water in, but I can put the aqueous in here and that shows us that it's with water. So my Ka is going to be the H plus times F minus over HF. I have my Ka value. Let's look at what's going on. Initially, they told me that I have 0.2 molar HF and I have 0.1 molar HCl. If you go back and you look at this, you were given 0.2 HF and 0.1 molar HCl. So we're not interested in the Cl minus, we're interested in the H plus. So that's why this is 0.1, this is 0, minus x plus x plus x. So I have 0.2 minus x, which I told you is technically 0.2, but you can leave it and put it in your solver, and 0.1 plus x, which is approximately 0.1, and x. So what might look different here is that you, if you're using your solver, as I did, will probably just put 0.1 plus x times x over 0.2 minus x. And then you solve for x. And you'll get approximately 1.4 times 10 to the minus 3. And this x represents the F minus concentration, which is right here. And to find the equilibrium concentration of the H plus ion, we have to add x to that. So you had 0.1 plus 1.4 times 10 to the minus 3. This number is so small, it's not going to have any bearing on the overall concentration. And then our pH is the negative log, so our pH is 1. Again, increasing the H3O caused the reaction to shift to the left, favoring the reverse reaction and slowing the dissociation of the hydrofluoric acid. Okay, let's talk about buffer capacity for a minute. I don't believe this is in your notes, but you should know what buffer capacity is. Buffer capacity is the amount of acid or base that can be neutralized by the buffer before there is a significant pH change. So your buffer capacity depends on the concentrations of the components of the buffer. The greater the concentrations of the conjugate acid-base pair, the greater the buffering capacity. And the pH range of the buffer is the pH range over which it's an effective buffer. So different buffers have different pH ranges. The pH range of a buffer is generally within 1 pH unit of the pKa of the buffering agent. And I just pulled out this sentence because it's the most important. The greater the concentrations of both the HA and the A minus, meaning the acid conjugate pair, the greater the buffering capacity. So what is a buffer? A buffer resists a change in pH. So what must a buffer have? A buffer must have a couple of things. 1, a weak acid, and 2, significant quantities of its partner. So in this case, we're talking about a CB, a conjugate base. If you're not sure what that means, please write it out. Now, it could also be a weak base and significant quantities of its partner. So in this case, the conjugate acid, Ca. For example, I might have NH3, which is a weak base, and I would have NH4 plus, which is its conjugate pair, also weak. The other thing that we have to realize when we're talking about significant quantities, we want a range of a magnitude of 10. So that's what we mean by significant quantities. For example, I could have the acetic acid, which is a weak acid, with a molar concentration of 1.0 molar, and I might have the conjugate base, which would be just the acetate ion, and that would be 0.1 molar. So this is considered significant quantities. Remember, to refresh your memory, the only difference between a weak acid and a base and its conjugate is the difference of a proton. So acetic acid and the acetate ion are conjugate pairs. We covered that in a previous lesson. This is not in your notes, but I felt it important to include. I just want you to understand what happens in a buffering situation. Most students refer to this part of the unit as blasted buffers because they're very difficult to understand. So buffers are basically a stoichiometry calculation. So this is what can happen. The addition of a strong acid or base obviously results in neutralization, because if I have an acid and I add a base, it's going to neutralize. So here I have my cation, my anion, and I add an acid, and it forms acid and water. Here I have my acid and I add base, and it forms the anion and water. By knowing how much acid or how much base was added, we know how much the acid or the anion was formed. It's an equilibrium concentration. With the concentrations of the acid, basically, and the base, taking into account for the change in volume of the solution, we can calculate the pH from the Henderson-Hasselbalch equation. And you're going to see this, you don't have to write this now, this is an equation that we're going to be using. So in this equation right here, I've added acid, and in this bottom equation, if anything, I would jot these equations down. I've added base. So I have an acid, I add base, and I get my anion and water. Here I have a base, I've added the acid, the H3O, and I get acid and water. The only way to get good at these problems is to actually do them. So the rest of this lesson and the next is going to be a whole lot of problem solving. Again, you must feel free to pause, check your calculator, make sure you're getting the same answers that I am. In this first example, it says, what is the pH of a solution where 50 mils of 0.5 molar sodium acetate is mixed with 25 mils of 0.25 molar acetic acid. So I'm going to write my equation, and I know that we've been on the acetic acid train for a while here, but we will come off it shortly and switch to others. I just felt it was important to do a couple with the same example so that you really understand it. So what's going on here? Well, let's set up my... In a buffering system, we don't really call it an... in a buffering system, we don't really call it an ice table. Sometimes we call it a before after change, a BAC table, but I think I'm just going to continue. So you might see this called ice, and you may see it called BAC. Okay, so it's just another way of looking at this. So initially we have to figure out what is our initial concentration. Well, you're mixing this with this, so we have to calculate the new molarities. So I'm going to do that over here. Okay, so we have to figure out the new concentrations because we're mixing the two solutions together. So let's do my acetic acid first. So this is my HC2H3O2. We know that molarity is equal to moles over liters. So I'm given 0.25 molar equals X over, and this would be 0.025 liters. So my X is going to give me, when I solve for X, I'm going to get moles. So this is going to give me 6.25 moles. Okay? That's my X. So molarity is equal to moles, 6.25 moles, over my total volume. So I've got 25 mils and I've got 50 mils, which is a total of 75 mils, which is a total of 0.075 liters. And that's going to give me a molarity of 0.083 molar. So that's what I'm starting with here, 0.083 molar. Now to that solution, I'm also adding the acetate ion. I'm not interested in the Na, but I am interested in the acetate ion because that's my common ion. So I've got 50 mils of 0.5 molar. So this is 0.5 equals X over 0.05. So X is going to equal 0.25. No, hold on. 0.5 times 0.05. Is going to be 0.025, 0.025. So 0.025 moles. And then I've got molarity equal to 0.025 over 0.075, which is going to be 0.33 for my molarity. So this is 0.33 for my acetate ion, and I have no hydrogen ion right now. So this is going to be minus X This is going to be plus x plus x. This is going to be 0.083 minus x, x 0.33 plus x. So, using my Ka value, my Ka of acetic acid, as I told you earlier, is 1.8 times 10 to the minus 5. And that's equal to 0.33 plus x times x over 0.083 minus x. When I put this into my solver, I get an x value, which is equal to my H plus concentration. It's also equal to my acetate ion concentration, but I'm not writing that down because the paper gets too cluttered, because I'm really just trying to find pH. And that's going to give me 4.53 times 10 to the minus 6 molar. And then we take the negative log of the H concentration, which will give us our pH. Therefore, our pH is equal to 5.34. And that's my final answer. As I said earlier, we have this cool equation called the Henderson-Hasselbalch Equation. And what this means is that you have a shortcut. And I know that you all love shortcuts. This equation, first of all, can only be used with buffers. How do you know you have a buffer? Well, I told you. You have to have an acid-base conjugate pair, right? So acid-base pair. And you must have significant quantities. You must have significant quantities. So here you say pH equals the pKa, okay? Anytime you see P means negative log. So basically this can be translated to pH equals the negative log of the Ka plus the log of the concentration of the base over the acid. Sheep say bah. Okay, so base over acid. I know, it was corny. So I want to use this equation to take all the work that we just did and make it a whole lot easier. So in our last problem, if we were going to use the one that we just finished, so pH equals the pKa, so that would be the negative log of the Ka, which was 1.8 times 10 to the negative 5. And that would be the base over the acid plus the log of the base. Okay, our base was our acetate ion. Now let's go back and make things easy for ourselves. Right before we converted this, I want you to look here. I'm going to use a different color. To make things easier, I'm just going to show you how we can calculate in millimoles to make things easier. So, calculations in millimoles. So basically what you do is you take your moles, to do your calculations in millimoles, you go back to your original equation. So for your base, you've got 0.5 times 50. Okay, so you've got 0.5 moles equals x over 50 milliliters. So 0.5 times 50 is going to give me 25 millimoles. And that would be over 75 milliliters. Millimoles divided by milliliters, okay, gives me molarity. So I'll put that over here millimoles divided by milliliters equals molarity. And this actually makes your life a whole lot easier. So this is my base, C2H3O2 minus. And my acid, I had, if we go up to our problem again, 25 mils of 0.25 molar. So now I've got 0.25 times 25, which is going to give me 6.25. So I've got 0.25 equals x over 25, which is going to give me 6.25 millimoles over 75 milliliters. And this is my acid. So I'm going to use this to show you how it saves some time. So going back to this problem, okay, plus the log of my base. My base is the acetate ion, which is going to be 25 millimoles over 75 milliliters, divided by my acid, 6.25 millimoles over 75 milliliters. Now I'm doing all this work just to show you what happens. So I can get rid of this and I can get rid of this. So basically I'm just taking my millimoles of my base and dividing it by my millimoles of my acid. So coming over here, I have pH is equal to the negative log, because this was the pKa of that. The negative log of the Ka is going to be 4.74 plus the log of 25 over 6.25. And I get a pH equal to 5.34. Go back to my problem. Lo and behold, a pH of 5.34, and I didn't have to do any of this work. So this is a really, really nice trick that we can use when we have a buffer problem. I do want to point out the fact that this formula is pKa. So if you're dealing with a buffer that is basic, okay, you have a problem. So if you have a base, then use the Kb to find Ka, because you know that Kw equals Ka times Kb. Now, I don't want to confuse you, but you could also rearrange this formula and you could have POH equals the pKb plus the log of the base over the acid. So technically you could use the pKb as it is, but you would be finding the POH, which then you would have to do 14 minus POH to get pH. There's a myriad of ways to do this problem. It's whatever works for you. Some students just like keeping the one formula, pH equals pKa plus the log of the base over the acid, and then they just find the Ka using the Kb. I can't tell you what works. You have to find, you know, what's your path of least resistance. Okay, I think I'm going to do 2 more problems, and then we're going to go into another lesson, which is just more problem solving. So calculate the pH of the following solution. We've got 25 mils of 0.15 molar solution of hypochlorous acid, which is HOCl, and 32 mils of a 0.45 molar solution of potassium hypochlorite. We're not interested in the K, we're interested in the OCl minus, which would just be the hypochlorite ion. So let's figure out what we have here. First of all, we need the Ka for hypochlorous acid, so the Ka of HOCl, when we look it up in the back of the book, is 3.5 times 10 to the minus 8. We need to see if we have a true buffer system here. We have 0.15 molar solution of hypochlorous acid, and that's 25 mils. So that's going to give me 3.75 millimoles. Notice how I'm working in just millimoles now. I did my molarity times my milliliters, which gives me millimoles. And for my hypochlorite ion, OCl minus, I have 0.45 molar, and I have 32 mils, which is going to give me 14.4 millimoles. So I have to say to myself, can I use Henderson-Hasselbalch? Well, I can, because I have an acid-base conjugate pair. They only differ by 1 proton, and I am within a factor of 10. So pH equals pKa plus the log of Ba, B over A. So pH equals the negative log, basically, of 3.5 times 10 to the minus 8 plus the log of my, now this would be over total volume. So if I were actually figuring this out, this would be 3.75 moles over 57 milliliters, and this would be 14.4 moles over 57 milliliters. So I think that you can make that intuitive leap that I can get rid of this, and it's just my base over my acid, which would be 14.4 over 3.75. So solving for pH, I get, when you plug this in, you should get a pKa of 7.46. So my pH is going to be equal to 8.04, and that's the problem. So this can be simplified if you are working in millimoles throughout the problem, which I've shown you. Working in millimoles works if the solution is a buffer solution. Let's do one more example, and that ends this lesson. Calculate the pH when 25 mils of 0.5 molar methyl ammonium nitrate, so here's our first component, is mixed with 75 mils of 0.3 methylamine. Methylamine, you might not know it, is methyl, so it's one methyl group, CH3, and the amine part is NH2. And the methyl ammonium nitrate, we're not interested in the nitrate, so the methyl ammonium ion is just going to be CH3NH3+. Again, we have a conjugate acid-base pair because they're differing by 1 hydrogen. Now we just have to see if they're within a factor of 10. So let's look at our base, CH3NH2. I've got 0.3 molar equals X over 75, which is going to give me 22.5 millimoles. And my CH3, my methyl ammonium, is going to be 0.5 molar and 25 mils, which is going to give me 12.5 millimoles. Well, I definitely have significant quantities, so pH equals, so we need the pKa here. Well, we have a couple of things going on. First of all, this is a base. Oh, I wrote this wrong. That should be NH2. Sorry to have confused any of you. All right, so this is my base. So the Kb of CH3NH2 is equal to 4.38 times 10 to the negative 4. I get that from Appendix 23. I'm going to solve for the Ka. I'm not ready to go down that road pH equals, or POH equals pKb. You want to do that, that's fine. Actually, I'm going to solve it both ways on this problem to show you. I didn't do it originally, but I will show you on this one because it's fairly straightforward. So to find my Ka, we're going to do, so Ka is basically going to be equal to Kw divided by Kb. So that's going to be equal to 2.28 times 10 to the minus 11. And then if I want the pKa of that, that's going to be equal, so if I take the pKa, that's going to be 10.64. So I just did right away, I just did the negative log right here, negative log of that, and I got 10.64. So pH equals 10.64 plus the log of the base. So my base is 22.5 over my acid, 12.5. And this would be over 100 total. I just want to show you that 75 and 25 mils is 100 mils. And I can get rid of that because they're the same, which is why I only have 22.5 over 12.5. So my pH is equal to 10.9, which should make sense because this is a basic solution and the pH is greater than 7. Let's set it up the other way. POH equals pKb plus the log of the base over the acid. So my POH is going to be equal to, so if I use my Kb over here, my Kb was 4.38 times 10 to the negative 4. Okay, so your POH would be the negative log of the 4.3, so pKb is the negative log of this, which is going to be equal to 3.36. So POH equals 3.36 plus the log of 22.5 over 12.5, which is going to give you a POH equal to 3.61, which actually gives you a pH of 10.4. So they're not exact, okay, but you can solve it either way. As long as you're showing your work, you're still going to get full credit. And I'm wondering why they're not as exact as they're not, and that's a question for a high. Okay, and that's going to end today's lesson.